Imagine you have just bought a new football jersey and a new pair of shorts. Now your collection grows up to 6 jerseys and 3 pairs of shorts. You might already be imagining, how does the Liverpool kid look with the beige shorts? How does the Barcelona kid look with the black shorts, or even with the grey shorts? And you might start to wonder, how many possible combinations are there actually? Well, let us count for ourselves. Let's use the jersey as the anchor. We have the Barcelona kit. It can be paired with the black one, the beige one, and the grey one. So there are 3 combinations for the Barcelona kit. Now for the Liverpool kit, you can pair it same as before with the black one, with the beige one, and with the grey one. So there are 3 combinations. And to think about it, each jersey can also be paired by 3 of the shorts. So all of them have 3 combinations. And since there are 6 jerseys, the number of possible combination is 3 multiplied by 6. If you don't believe me, let's do it the other way around. Now the pair of shorts become the anchor. This black pair of shorts can be paired with the Barcelona kit, with the Liverpool kit, with the PSG kit, with the Portugal kit, Real Madrid kit, and with the Mexico kit. So there are 6 possible combinations for the black shorts alone. The other ones, they can also be paired with 6 of the jerseys, so 6 as well. And since there are 3 shorts, it's 6 multiplied by 3, which gives us a grand total of 18, the same result everywhere. And this principle is called the principle of multiplication, which is the foundation of combinatorics. Today we will be learning about factorials. Factorials basically ask a question: how many ways to arrange things? For example, I'm going to ask you how many ways we can rearrange these children standing in a line. We can rearrange it this way, and many sorts of ways. But how many are there in total? Let's try to figure it out. Well, we can think of the lines as 4 spots for them, right? Each one of them can stand on the first spot, second spot, third spot, or fourth spot, doesn't matter, right? Now let's take a look at the first spot. How many children can we choose to stand on that spot? Easy, 4. Well, because there are 4 children. But because we have already chosen one of them, then our choices has gone to 3 only. So now the next spot can only be occupied by 3 children. Will not be occupied by 3 children, but there are 3 children that we can be choosing. And again, same process. So the next one is 2, and the next one will be 1. So we can just multiply this to get the end result. And this process is called factorials. And it is denoted as 4 exclamation mark. 4 factorial basically just means 4 times 3 times 2 times 1. So it's a number multiplied by the preceding number. So it's multiplied by the numbers below it until we get to 1. So 4 factorials, 4 times 3 times 2 times 1. And then 5 factorials, 5 times 4 times 3 times 2 times 1. Now you might be wondering, is there a 0 factorial? The answer is yes. But it might not make sense to you because, well, we're trying to multiply downwards until we get to 1. A 0 is already below 1. But that's a wrong way of thinking it. Because remember, the basic concept of factorials is how many ways we can arrange stuff. Let me ask you this. How many ways are there to arrange nothing? You might be thinking, 0? That's wrong. Because having nothing itself is already a way of arranging it. If you don't understand what I mean, think of an empty room. How many ways are there to arrange the furniture? Well, there is one way. And the only way is to leave it as it is. Which is why having nothing itself is already a way of arranging it. So 0 factorials equals to 1. Now that you already get the basic of factorials, let's get the real problems. How many ways are there to arrange the word lumina? Well, first of all, let's see how many elements are there. How many letters? 6. So we prepare 6 spots. Same process as before. First spot can be chosen 6 letters, second spot 5 letters, and so on. So 6, 5, 4, 3, 2, 1. Apply the principle of multiplication, which is 6 factorial, and get the answer 720. How many ways are there to arrange the word maths? First, count how many elements are there. In this case, 5 letters. So 5 factorials, which is 5 times 4 times 3 times 2 times 1, which is equal to 120. How many ways are there to arrange the word even? Well, again, 4 letters, 4 factorial, 24. Yeah, 4 factorial is 4 times 3 times 2 times 1, which is 24. But honestly, I'm a bit skeptical about this. It doesn't seem right. Can we get a fact check here? I have tried to rearrange everything, and turns out there are only 12 possible rearrangements. So, what do we do wrong here? Well, let's take a deeper look on the word. There's one property that this word have, but others don't. Well, the previous one don't. Is that we have repeating letters. Now, rearranging something doesn't mean we have to completely flip all of the letters. E has to go to the back, N has to go to the middle, and everything. No. Rearrangement can even occur when we only swap 2 letters, like V and N. Let's swap them. NF. I don't know what that means, but it's a new word. So let's see in the case of even here. This E, the red E, and the blue E can be swapped together. Yes, it is a new arrangement, but is it a new word? No, they're still even and even. So they're the same. So we're overcounting. We count those that aren't even supposed to be counted. So we have to cancel some of the unnecessary countings we have done. By doing what? Well, by observing the same letters, this is repeating letters. How many ways are there to arrange them? Since there are 2 E's, then 2 factorials. So we have to cancel these. Now, how do we cancel these? You might be tempted to think, oh, just subtract them. Wrong. Because subtraction and multiplication doesn't belong together. Think about it. If you want to cancel addition, you subtract them. So if you want to cancel multiplication, we have to divide it. So 4 factorials divided by 2 factorials, which is equal to 4 times 3 times 2 times 1 divided by 2 times 1, which is equal to 24 divided by 2, which is 12. Now this aligns with what we have counted annually. If you don't believe me, try it for yourself. Let's try again. How many ways are there to arrange the word banana? Well, let's check for repeating letters. We have 3 A's and 2 N. We just have to set them aside for a while, and let's continue. How many letters are there? There are 6 letters. So, 6 factorials. Now let's set our focus into the repeating letters. The double N's. There are 2 N's, so we have to cancel 2 factorial. So, 6 factorial divided by 2 factorial. Now, the triple A's. Since there are 3 A's, we have to cancel 3 factorials. So, we divide it again by 3 factorial. Voila! 6 factorials divided by 2 factorial, divided again by 3 factorials, which just means 6 factorials divided by 2 factorials times 3 factorial. And we can just work this way out. 6 times 5 times 4 times 3 times 2 times 1. 2 factorials is 2 times 1. 3 factorials is 3 times 2 times 1. You might be tempted to just multiply the top and then multiply the bottom and then divide it, but come on, there's a quicker way to do it. Notice how the 3 and 2 and 1 is repeating. We can just cancel them out. Much easier, isn't it? 60, the answer. In fact, this trick is always used to count factorials. Let's say we have 10 factorials over 7 factorials. This is such a big number. 10 factorials is so big. Like 6 factorials is already 720. Imagine 720 multiplied by 7, and then multiplied by 8, and then multiplied by 9, and then multiplied by 10. That's too much. So what do we do here? Well, 10 factorials is 10 times 9 times 8 times 7 factorial. Why is it times 7 factorial, not times 7, 6, 5, 4, 3, 2, 1? Well, remember, 7 factorials itself mean 7 times 6 times 5 times 4 times 3 times 2 times 1. So this is complete. Now we can just cancel them out. Voila. Now, the big flaw of factorials is that it usually only works in a straight line, in which there's a front and an end. Because why? Well, we can just rearrange things like this. We can just bring the last one to the front, and it's a completely new arrangement. But that isn't the case for something circular. If you have a setting of circle like this, how can we do it? Because where's the last kid located? Is it this guy? Is it this girl? Is it her? Is it him? No, there's no last kid. So how do we do it? Well, first we can just lock one kid up. Now notice how this kid acts like a barrier. The other ones now are in a straight line technically, and they can swap places easily. So how many other are being arranged? Only 3. So 3 factorials. So in the case of a circle, we always have to minus 1 before it. Now, you might be wondering, why am I teaching from the basics of the basics? It is because math is a game of logic, especially combinatorics. This is the heavy emphasis is on logics, because the more you climb up the level of combinatorics, the more you're going to encounter a situation where you have to use your higher order of thinking skills. You have to think more. And you cannot really think well if you don't even know the fundamentals, if you don't even know the meaning of every bit. Let me give you an example. I have all sorts of sort equipment. Now, how many ways are there to arrange these if the balls have to be together? I'm going to give you some time to think. Well, if your first thought was to group the balls together, you're on the right track. Now let's group them, and since they're in the group, they have to move together every time. Now, since they move together every time, we just have to consider this as one element. So in total, there are 5 elements. The group of balls, the gloves, the bat, the cleats, and the racket. So it's 5 factorials. But there's one important detail that you might be missing. If you notice, inside the group of balls, there are 4 elements, and they can swap places too. They can be rearranged too. Since there are 4 elements in the group, they can be rearranged too, giving us 4 factorial. Now the question is, does this 4 factorial add the number of arrangement? Does it make the number of arrangement bigger, or does it make it smaller? In other words, did we overcount or did we undercount? Let's see. Well, if we just consider this as one element, then we would think this as one arrangement. But remember, this can be rearranged one more time. Well, not one more time. We can rearrange them multiple of ways. So really, we are undercounting it if we only consider this as one element. So since we're undercounting it, yes, it does add to the number of arrangement. So instead of cancelling it out, we have to reinforce it. So we have to multiply it by the previous number, and it gives us 2880. So that's all about factorials. I hope you understand what I have explained to you, and if you want to practice, there's a free worksheet available in the description box. Thank you so much for watching. I appreciate your time, and I hope to see you in the next video.